Hello? Do you hear me?
Yes.
Hello, Costanzo.
Hi.
Hi. Do you hear me?
Yes.
Where are you?
I'm fine. You?
Fine, fine.
Possiamo parlare anche in italiano.
Yeah, but we have a lot of Russian people in this session.
Yes.
Yeah, yeah. Hello, Filippo. I think that we can start. There is.
Ciao Giacomo.
Yes. Ciao, Filippo. Okay. Welcome. This is the session number 7. I can start. Can I start? Okay, I am.
Ciao.
Ciao.
Penso che mi conosci, mi conoscete tra me e loro, mi conoscete per alla Simpson. Okay, we can start, I think. Okay. Hello, Anna. Okay. Let me introduce me. I am Giacomo Resitano from Messina University. I am an assistant professor in the machine design. I am the chairman of this session. It's session number 7. We have 12 presentations, 10 minutes per presentation, only 2 minutes, 3 minutes for a short presentation. After we have some questions for the authors. I think that is better to start. And okay, the first work is by Ebsta Feva Pronina. Sorry for the pronunciation, the surname and the Russian pronunciation. Sorry. The title of the speech is 18-walled pipe exposed to corrosion under pressure and under non-uniform heating. I don't know if Irina or Julia. Okay, Irina.
Good afternoon.
Good
afternoon, dear colleague.
You can show your presentation, short presentation.
Yes, thank you. I have some slides. May I show it?
Okay.
So,
1 minute. Okay.
We consider linearly.
Yeah. Okay, you can start.
We consider a linearly elastic thin-walled pipe exposed to mechanochemical corrosion and internal and external pressures and subjected to different temperatures. As shown in our paper, using the classical thin shell model for the problems of mechanochemical corrosion can lead to a significant error, especially when the common part of the internal and external pressures is large enough. We received new solution in the form which is absolutely the same as the existing solution based on the classical thin shell model, with only constants being different. At the same time, our new solution reflects the effects of hydrostatic pressure, change in the hoop stress through the pipe wall thickness, and of the temperatures, and demonstrates a perfect coincidence of the results with the explicit solution, which is rather cumbersome. So that's all what I wanted to say.
Okay.
About our results.
Okay. Thank you for your short presentation. Thank you. Are there some questions from the participants. 1 minute, I try to understand if there is a question. Okay, I have some question for you, Irina. The first is that if, do you have calibrate your analytic solution with some experimental testing, or you think that you can calibrate in the future?
So now we didn't calibrate our analytical solution with experimental results, but further we will try to do it, maybe.
Okay.
Maybe I can answer because I'm co-author.
Yeah.
The model that we used for this solution is phenomenological based on the experimental results for simple samples. And
Okay.
for one-sided or two-sided tension, and for the pipe, the same experimental testing couldn't be rearranged, so it's not possible.
Okay.
It's the only way to apply the non-experimental results to such
Okay.
pipes.
Thank you very much. Can I want, if possible, I have to ask another question. And in your opinion, do you think that it is possible to integrate the stress fatigue problem with your solution?
In this solution, of course not. It's impossible because it's another problem, and we try to tackle this problem, yes, with other postgraduate students.
Okay, thank you. And do you think it is possible to do a numerical model to calibrate your solution, non-experimental, but numerical? I think to FEM, for example, it's possible. Is it possible?
Of course, it's possible, but it's not. There is no any need for this because this is analytical solution that is exactly satisfy all the equations and all the boundary and initial conditions. So it's this solution can serve as a benchmark solution for finite element and other numerical solutions to verify them, because the problems of mechanochemical corrosion is coupled problems and with a priori unknown boundaries, and they hard to model numerically. And even in top-rated journal, there is articles with wrong solutions, numerical solutions, and so there is a clear need in this analytical solution to verification of numerical solutions.
Okay, thank you very much for your talk. Thank you, Irina. Thank you, Professor Pronina. And if there is other question, are there other question from our speakers? No. Okay. Thank you. Thank you very much.
Thank you.
I hope to see in other better situation in live. Okay, we have the second presentation. The title is Analysis of the Durability of a Functional Coating Against Glass Stress Corrosion by Mariggio, Dalle Vacche, Bongiovanni, Corrado from Polito. Please. I leave my chair and I...
Thank you. Hi, everyone. Really thanks to the chairman for the nice presentation. And I'm Gregorio Mariggio, and I'm going to talk about the performance of innovative functional coating against stress corrosion. Thanks. Okay. The study was conducted in collaboration with Dr. Sara Dalle Vacche and the professor Mauro Corrado and Roberta Bongiovanni. Let me start talking about stress corrosion mechanisms in soda lime silica glass. Stress corrosion, also known as static fatigue, consists in the reduction of the glass strength caused by the combined action of applied stress and humidity on the silica network of glass. Mikulski and Freeman developed a detailed chemical model to explain the interaction of water with the silica network at the crack tip of the glass. The reaction involves 3 stages. At the first stage, water approaches the silicon-oxygen bond at the crack tip. In the second step, there is a transfer of electrons and protons with a concerted reaction among atoms, resulting in the rupture of the original bridging bond between silicon and the oxygen and the formation of 2 new bonds, one between hydrogen from water and oxygen, and one between oxygen and silicon. Finally, we have the rupture of the original bridging bond and the formation of 2 new fracture surfaces. The goal of the study was to limit the effect of stress corrosion and the effect of humidity on the glass mechanical performance. This was done by the application of a UV-cure coating on the glass surface. The UV-cure coating was developed with a compositional profile to maximize hydrophobicity, barrier to water vapor, and adhesion to glass. The production of the coated glass samples involved 3 steps: silanization of the glass, application of the coating on the glass surface, and UV curing of the coating. Several properties of the coating were assessed, including transparency, wettability, barrier to water vapor, and adhesion to glass. The effectiveness of the coating was evaluated by comparing the viable distribution functions of the bending strength of coated glass and uncoated glass. As we can see from the graph, coated glass was the least affected by stress corrosion, as its viable distribution functions was the most shifted towards higher stress values. Finally, the durability of the coating was assessed by comparing the bending strength of aged coated glass with that of uncoated glass. 3 scenarios were analyzed in terms of aging: mechanical aging, natural weathering, and artificial weathering. In conclusion, the current formulation of the coating can be used for practical application, as it has shown a very good performance in terms of effectiveness, durability, and reliability. Thanks for your kind attention. I will be happy to answer to your question.
Thank you.
You're welcome.
Okay, the discussion is open. Are there some questions? Okay, I have some questions for you. I see your long presentation, and it's very interesting work. My first question is, what was the test frequency during the cycling test, and why you use because I don't understand the frequency.
Yeah, the frequencies during the mechanical aging. Yes. So the frequency that we used during the
cycling testing.
During the cycling testing, so yeah, we use a frequency of 3 Hz. No, there isn't. In fact, there isn't a specific motivation, because we can choose, and we can choose other kind of frequency. But the frequencies was important, should be important if the glass were subjected, if the glass was subjected to stress corrosion. But we applied on the glass surface a coating, so we think that the coating completely prevent stress corrosion. So the duration of the test, so the performance of the glass should not be affected by the duration of the test.
Thank you very much. I have another question. The usability of the clotting has been investigated, okay, in your work.
Yeah.
In your opinion, is it possible to do an analytic solution of the problem to understand the future behavior of this type of materials?
Yeah, why not? In the future, we want to perform analytical analysis to understand better the behavior of coating, the behavior of coating and the coating that was applied on the glass.
And if you think that it's possible to do a numerical model, because it's not easy when there is a type of solution. But if you do, you can have time, a lot of time you can use for others.
Yeah, unfortunately, this numerical analysis wasn't done in this study. But in the future, maybe we'll perform numerical analysis. I think that it is not an easy matter. I agree with you.
I think that don't stop now.
Yeah, no. We want to perform other aging process and also numerical analysis.
Thank you. Thank you.
You're welcome.
There are other questions from our speakers, from other person? No? Thank you.
Okay, you're welcome. Bye.
Okay. Allora. Okay, we have the third presentation by Nutta, Tridello, Bellingardi, and Paolino. The title is an innovative non-destructive technique for the local assessment of the residual elastic properties in damaged composites. Presents in live. Okay. Okay. One moment for the other person. Yeah. Ok. Clicco comunque. No, continua senza analizzare. Dimmi tu. Ok. Dobbiamo però ripristina. Mettiamola sopra la sì, forse è meglio. Sorry, annulla. Facciamo così, IGF dicevi. Ci mettiamo qua. E così migliora. Sì, migliora. Te la metto in presentazione. Anzi, facciamo una cosa prima. Sorry, one moment for all, because I have to share, I think. Condividi lo schermo. Ok, condividiamo questo. Condividi. Ok. Ok.
Good afternoon, everybody. I'm Carlo Borsier from Politecnico Torino, and my study concerned the development of an innovative non-destructive technique for the local assessment of residual elastic properties in damaged composites. Okay. Damage in composites is characterized by a complex multitude of cracks, which can arise from both the manufacturing process or during the service life. And also the prediction of the evolution difficult and case dependent. These observations suggest the need of assessing the damage severity in terms of material response in presence of damage or flows, rather than in terms of extension of the cracked area, as usually done in current non-destructive techniques. And the degradation of the elastic properties is the macroscopic result of the damage. So we aim at developing a non-destructive technique able to assess the residual elastic properties in damaged composites. And the method intends to isolate a region of the component by clamping the boundaries. And in this way, a specific mode can be excited, as you can see here in the figure. And from the measurement of the first resonant frequency, the elastic properties of the retained region can be assessed. Here you can see the experimental setup, where in order to non-destructively clamp the boundaries, the vacuum is adopted, and the region under investigation is the one comprised within the internal seal. The technique is also characterized by a mapping procedure, where the device is moved on the plate in order to obtain different measures of the frequency. And this also highlights that the frequency reduction was proportional to the participation of the damage to the mode shape. The higher the modal participation of the damage, the higher the reduction of the frequency. And from this observation, we were able to calculate the elastic properties specifically of the damaged region. To validate the technique, we consider two composites, one made of 6 layers and the other one with 8 layers, with made of glass fiber and epoxy resin, that we realized in our laboratories in Polytechnic di Torino, and that we damaged by impact. Then we applied the non-destructive technique, and then we, to validate it for comparison, we performed tensile tests on specimens that we cut from the plate and that we kept it with the optic fiber in order to obtain a punctual measure of the strains. And these are the results for the 6-layer plates, where you can see that the reduction of the frequency is proportional to the modal participation of the damage. In particular, the highest reduction is obtained when the damage is in the center of the device. And here from the tensile test, you can see the results of the strains with the in correspondence of the damage. There is a consistent decrease of the elastic properties. And also by comparing the non-destructive technique with the optic fiber results, you had that the discrepancy is very, very limited. And the same conclusion can be drawn also for the 8-layer plate, where again, the reduction of the frequency is proportional to the participation of the damage to the mode shape. And again, the reduction of the elastic properties can be clearly, consistent. And again, the discrepancy is very, very limited, which validates the technique. And that's it from my side.
Okay, thank you very much for your presentation.
Thank you.
Okay, are some questions? What is your name?
Carlo.
For Carlo? From our speaker, from our platea? No? Okay, I have some questions for you.
Yeah.
Because I see your extended presentation.
Yep.
Very interesting work. I like very much.
Thank you.
And okay, the first question is: do you think it is possible to do a numerical model, a model of your experimental testing?
Yeah, I tried to. The problem is that the modeling of the clamping system, because you have that. I can go up.
Yeah.
You can see that the clamping system is realized through vacuum, and here you have the contact between the plate and the system is through this rubber, the seal rubbers, and which have non-infinite stiffness. That's why the modeling of this part can be a bit critical, but it can be done.
It is critical because you need good replies of the experimental test, because I see that you have you do some frequency testing, and if there is another boundary condition, it's not easy to reply the experimental. Okay.
That's why actually the technique involves some analytical procedure where we can, let's say, avoid the specification of the boundaries, let's say.
What software do you try to use for the FEM?
Let's Dynamical. More or less.
A good software. In your opinion, is it possible to apply this technique to other materials? Because your materials is specific materials, okay?
Yep.
But I think so. Yes, you can, but I don't know because it works your.
I would say that if you're thinking about metals, then maybe there is not that much the interest into applying that, because in the case of metals, it's more important to know the extension of the crack rather than the residual elastic properties. And for talking about other composites, well, it is part of the future work. In this case, we consider, let's say, one simple composite because it was a woven fabric. Maybe we can switch to laminated made of unidirectional plies or also short fibers in the future.
This work, is it this work in collaboration with some industries, or is only research?
Yep, research activity.
Okay. Very interesting, but I think that some industries are interesting to your work. Okay, and it's not a question, it's only the device for other researchers that wanted to reply your testing. What is the most difficult to do to reply your experimental testing?
What do you mean? Sorry.
For example, I don't know if the system, the measure system, or are difficult to have the specimen. What is the most difficult tools that you have during your experimental testing? If you have to do an advice to other research, you can see that you have to open your eyes to, for example, for the problem with the frequency or the F. I think that I see that you make a fast Fourier transform, for example. I work on the frequency on this material. It's not easy. It's not easy to interpret the fast Fourier transform.
No, right. However, I would say that the most difficult part is the understanding of the experimental result, in the meaning that if you start thinking that this is clamping a region, so you start thinking that that is a perfect clamping, and instead in reality it is not a perfect clamp because you have not an infinite stiffness on the boundaries, and that is the most difficult part.
Thank you very much.
You're welcome. Thank you.
Bye, Carlo. Thank you. See, of course. Un momento, mi stop all presentation, interrompi condivisione. Posso stapparla brutalmente? Ho perso tutti i dati. Okay, we have the number 4. Okay, from Azzadi, by Azzadi e Arro. The title is Sensitivity Analysis of Stress, Pre-Corrosion Nanoparticles, and Heat Treatment of Fatigue Lifetime of Aluminum Alloy. I don't know if there is Mohamed or Anik. Azzadi? Arrow? Are you here? No? Okay. 1 minute, but I think that Mohamed or Anik. Okay. If Mohamed and Anik are not here, I think that it's better to go to the next presentation by Fesenko Weisfeld. Sorry for my pronunciation. The title is The Dynamical Problem for the Infinite Elastic Layers with a Cylindrical Cavity. Anna, I see you.
Yes, yes, okay, I'm here. I'm here.
Hello.
Hello.
Okay, hello, I see you. Okay, you can share. Okay, you share. Perfect.
Shared, okay.
You can start.
Let me present you. My name is Fesenko Anna. I'm from Ukraine, Odessa National University, and this work was developed with Professor Natalia Weisfeld. In our department, in general, we work on different elastical problems. Especially, we can take into account volume forces, temperature, and considering it with different boundary condition, so as presence of different defects, such as cracks or inclusions. Here in our work, we solved the problem with cylindrical cavity. It can be considered also as a tube, for example. This method was proposed and developed by our prominent scientific leader, Popov Gennady. And it is about application method of integral transforms to the initial problems. And after that, we can get a vector boundary value problem. And after it can be solved using matrix differential calculus. We consider it this statement a dynamical statement. So in the surface of the cavity, acting dynamical force. Both layer side can be or fixed, rigidly fixed, or can be supported as a foundation without friction. When conditions of smooth contact is given on the both layer sides, can be obtained an exact solution. When sides are fixed, this problem was reduced to integral singular equation, and so this solution was approximate. The uniqueness of this method that all calculation was, all unknown function was matrix. So we applied here a method by Popov, developed by Popov, and constructed all given function such as Green's functions and basis functions matrix using this matrix calculation. After obtaining this solution, we was interested in calculated stress that appear near the cavity surface on the fixed side of the layer. And we consider different types of acting loads on the cavity surface, such as parabola branches down or up and distributed according sinus law, like in these pictures. And we consider different types of frequencies. For large frequencies, we had to construct asymptotic formulas because of presence of one second, because of presence imaginary parts under square roots. We had to construct asymptotic formulas for different cases, natural frequencies. In brief, I think it's all.
Okay. Okay, conclusion. Do you have a finish?
Yes.
Okay.
Brief,
okay.
I'm finished.
Okay, okay. Thank you for your presentation. I see your long presentation on YouTube before, of course, this session. And are some questions from our speakers, from our online friends? Okay, I have some question for you, if for you is okay. My first question is, do you think it is easy to apply your proposed approach to solve a elasticity problem with a different boundary and initial condition?
Yes, of course, this method is applicable for different boundary conditions. For example, we've already solved an analogical problem when inclusion is in the layer. And I'm also interested in the previous report in previous section when you've made an experimental, and I thought that it can be considered, for example, such as inclusion that go to the tube, but maybe in this case we must consider also influence of temperature. Maybe like an inclusion that has some temperature and what tensile can appear, what stress can appear in maybe near zone of this inclusion in the layer. And also we would like to consider when we have some layers that that connect in one side, maybe it would be interesting too.
Okay, thank you very much. And in your opinion, what is the limit of your approach, your proposed approach?
Limit?
Yes, where you cannot use.
In our work, we try to, we deal with, I can say, pure mathematica. We have no opportunity to make an experiment. And we try to find exact formulas, and we have such as complicated expression under integrals, and calculation is I can say difficult because we have a presence of cylindrical functions, function of heavisides, and after that we turned it into McDonald functions and infill functions, and we was interested to have a mathematical formula that represent this situation. We have no opportunity to make an experiment. Of course, it would be interesting to take a finite layer, not infinite like we have. But in this case, if we want to apply this method, we should apply method of finite integral transforms. And in this case, we had to, when we will inverse it, it would be difficult to get formulas. And also we perform Laplace transforms, and it's known that it's difficult to inverse. And we considered the case steady state oscillation and took natural frequencies. But it's interesting to take general formulas. It's in the progress, maybe.
My third question is connected with what you say now. For you in the future, is it impossible to calibrate with experimental testing your approach?
Yes, it would be interesting. Maybe it's my dream.
Okay.
Thank you.
Thank you very much, Anna. If I don't know, if are there some other questions from our online friends? No? Thank you, Anna.
Grazie
Bye.
mille per your attenzione.
No, grazie a te. Grazie a te. Okay. The presentation number 6 is by Maisov, Weifeld. The title is The Dynamical Stress Concentration Near a Cone-Shaped Crack in a Twist Truncated Elastic Cone. Are the Mason or Weisfeld?
Yes, I'm here. Hello. Can you hear me?
Okay, I hear you. You can show your monitor, your presentation, little presentation. Okay,
Yeah,
I see.
Short part of my presentation. My work is about the dynamic stress concentration near a cone-shaped crack and truncated elastic cone. It was done in collaboration with my scientific advisor, Natalia Weisfeld. So, in short, in my work, research was done for a twice truncated cone with a conical crack inside it in a state of steady-state torsional oscillations. The solution is constructed as a superposition of continuous and discontinuous solution. Also, the solution was derived with the help of integral transforms and by solving integral single equation with method of orthogonal polynomials. Here you can see some of the results. So for results, the wave field of the cone was found, and for example, here is stress intensity factor at the bottom edge of the crack. Here we move, for example, we move the crack same size in the middle of angular coordinate theta from bottom spherical face of the cone to the middle, and we see that when it's close to the spherical face, the stress intensity factor is higher, and here is same for when we move the crack to the lateral surface of the cone. We can see here that it is higher when we approach the border. So also we can see that the overall values of stress factor is higher when we cross the border, which is on which we apply the stress. So that's in short, like, and thank you for attention. Any questions?
Thank you to you. I see your long presentation before. I don't know if there is some question from our speakers or friends. No? Okay, I have some question similar to Anna, because your work is different, but with similar approach. My first question is if do you think it is easy to use your approach to solve problem with different boundary initial condition?
Yes, it's possible. I've previously tried for when rotating the cone over the lateral surface, not through the Cylindrical overlay. Also, I've tried I solved problem with when there is another type of crack inside cone. There is spherical, so there is possibility to solve it for other cracks, but they're not very good fit in spherical coordinate systems. So it will be just cumbersome calculations and formulas. So yes, it's possible to make this approach for other conditions.
And what is the limit?
The limit, well, the limit, I mean, there is also like cases, for example, that cone
Limit to use
repeat, please. Didn't hear.
Okay. Okay, I have another question for you. If in the future you think do you think it's possible to calibrate your analytic solution with experimental testing?
I would like to have that possibility, but we don't have such luxury to make it experiments.
Okay. Thank you very much. If I don't know if there are another question. Thank you very much for your presentation. Okay. we can go to the next presentation by, sorry for the pronunciation of the surname, Sanekov, Mikami, Kim, Ster,
Yeah.
Joe, Baksevanavki. Sorry, Nikolai, sorry.
Don't worry, it's okay.
And the title is Experimental Study of MG6 Alloy Mechanical and Ballistic Characteristic at different temperatures and the loading speeds.
Yes, so you can see my
I see your short presentation. You can start.
Thank you. So today I will present the study, the experimental study that was made on ALMG6 alloy. So the study was divided on 2 parts. The first part, so the first part was, so do you see how I'm changing the slides or no?
No,
Okay.
no, see.
So the study was divided on 2 parts. The first part of the study was devoted to, so we was in need to obtain the mechanical characteristics of the aluminum alloy. So we use for these 12 standard specimens, and so here are the characteristics, the geometrical and mass characteristics, and also we took 4 rectangular plates as a targets to test them during the high-speed collision, and we was trying to obtain the ballistic limit for this material also. So as you can see, we made 6 groups of experiments for different loading speeds, which were near to the, I think, to the quasi-static loading with the slight differences, and for 3 different temperatures: the ambient temperature of 25 Celsius, 75, and 150 Celsius. So we obtain the stress and strain diagrams, and we have evaluated the values of the maximum loads and the stresses and strains at the maximum loads for different types of loading speed and conditions and loading conditions. So as you can see, in comparison with the ambient in the ambient conditions, when we rise the temperature up to the 75 Celsius, our maximum stresses and strains slightly increases, and then when we go to the 150 Celsius, they decreases to some degree. So at the second part of the study, we made the ballistic loading with our test rig, which allows us to obtain the kinematic characteristics of the specimen, of the projectile, of the different types of the projectiles, and also this test rig allows us to obtain the dynamic stress and strain and displacement fields using the DIC method, digital image correlation method. As you can see, the ballistic limit, the obtained ballistic limit was somewhere between 171 meters per second, and we are planning to use this data, or we hope that someone can use this data to fine-tune or start to tune their mathematical models of the collision process of the rigid spherical projectile and this alloy. We also obtained and have time displacement dependencies for different points, for the point of the collision, for the point on the top of the specimen near the clamping, and also we have the time dependencies of strains in YY and XX directions. So this is my short presentation. I hope you have some questions. Thank you.
Thank you, Nikolai. Are some questions from the speakers or other person from our friends? Anna?
Can I ask a question?
Of course.
Can this problem be set in a mathematical statement as, for example, heat of the ball into the strain plate, for example?
Please, can you repeat?
Can we mathematically formulate this problem as a heat of a ball, for example, into the strain plate?
Ooh. So I think you can, but I can't really imagine how to do it.
Okay.
Sorry,
Okay, thank you.
imagine. Thank you.
I see our problems. Some department investigate problems pure mathematic.
Yes.
And another an experimental.
Yes.
And it's hard to talk about.
Sorry, I'm not very
because...
good in mathematics. I'm like the experimentator, the engineer.
Oh, okay, thank you. It's interesting.
Maybe I can help you with the experiments you need to provide to have some data. So
of course.
It would be interesting. I can help with mathematics.
Great.
In theoretical part.
Thank you.
I think that is better because the conference born for this type of connection, and it's a good idea.
Thank
okay, our other question? Nikolai, I have some question for you. The first, I appreciate very much your work because I love very much this type of field, of research field. And I think it is very interesting. My first question is, do you think it is possible to do a numerical model of your experimental testing? Because
yes.
I see some of another papers.
Yes, so I need to clear something that this work was like the preliminary testing for the next much bigger step when we were trying to understand how the asymmetrical thin projectiles collide with the targets of made of this alloy. And so the model is already done by our colleagues from Loughborough University, by Theo Stergio and Konstantinas Baksivanakis. They also did some calculations, and I hope we will. And there is a paper was published in this month, at the beginning of this month, devoted to the next step of this experiment.
Okay. When this paper is online, can you send me?
Yes, I can. It is already online. It's available. It's in Scopus. I can send you right now the link, I think.
Thank you. Okay. I have another question. In your opinion, I think, is it possible to apply this technique to other materials?
Yes.
Different.
We already have some experience. We did a lot of tests with the polymer composite materials, with layered composite materials, and also with different projectiles, as I said, spherical, flat, cylindrical, made of different materials, of ice, of rock, or some silicone.
Because I think it's very interesting for other material, for example, in other field, I don't know, in military field.
Yes, I think it's interesting. Yeah.
Okay, I have not. It is not a question. Is only my curiosity. Do you know how much all experimental setup cost?
It's yes, I know. It's about,
because I think it's very expensive.
So this setup the pneumatic gun and the DIC
and camera
and
and
cameras. I think it's about
1 million, I think.
About 700,000.
I think
less than 70% of the million.
So. Okay, thank you.
Okay.
Okay, it's very interesting.
Thank you very much.
Are some other questions from other person? No? Okay, thank you very much, Nikolai.
Great, thank you. Goodbye.
Okay, we have the other presentation. Okay, by Uvarov, dynamic and quasi-static interlaminar shear straight of carbon fiber laminate under biaxial loading conditions. Uvarov. Uvarov. Is there Uvarov?
Сергей, добрый день. Good morning. Good morning.
Good morning, Irina. But we want Uvarov. No? Okay. You have to go to the next speech and by Banikova, Irina, and Uvarov, scaling law in fragmentation dynamics of rock materials. Please, you can show your little presentation, your short presentation. Hello, Irina. You can show your...
Good day, ladies and gentlemen. I cannot my presentation.
We don't hear you.
Because
okay.
I maybe present it without my presentation.
Okay.
Okay.
If you if you don't have the short presentation, we can speak about your long presentation.
Okay. Short presentation without presentation. I am presenting a report scaling laws in fragmentation dynamic of materials, which was carried out at the Institute of Continuous Media Mechanics, Ural branch of the Russian Academy of Science, in the laboratory of physical foundation of strength.
I think I have some problem with the connection. We don't hear you. Irina? I think that is no easy to present from the car. Image, that is the problem. Can you hear me? Because we don't hear you. Okay, I think that there is some problem with our friend Serena. Okay, I suggested to go to the next presentation. After the end of all, we can try to reply with Irina. Okay, the next presentation is by Schomburg, Meltz, Blaker, and the title is Influence of Compressed Hydrogen on the Fatigue Behavior of a Ferritic Stainless Steel. Okay, I think that is better that we have a 5 minutes stop. We can try to. Okay, if there is the next presentation or other two next presentation. The last two presentation, if there is okay, see you. Nikiforsis, Ujikovsky, sorry for my Russian language, Zivirko, Turiluski, and Keskov. The title is Pipeline Durability and Integrity Uses at Hydrogen Transport via Natural Gas Distribution Network. I see your presentation. You can start, please.
Good afternoon. Thank you, Mr. Chairman. Thank you for introduction. All co-authors are from Ukraine. Title of our presentation is Pipeline Durability and Integrity Issues at the Hydrogen Transport via Natural Gas Distribution Network. As you know, that the new trend is now to use hydrogen as fuel in industry, and it caused some challenges in the different aspects, namely hydrogen transportation via pipelines. As Ukraine has extended network of natural gas transit pipelines from Russia to West European countries that could be used for supplying hydrogen for industrial application. However, we should take into consideration from this point the operational degradation of long-term exploited pipelines. Age of these pipelines is more than 30 years. A significant decrease of mechanical properties of operated steels, mostly brittle fracture resistance, can finally cause structure failure. In our presentation, the durability and integrity issues in existing natural gas pipelines with hydrogen are considered. And durability and integrity issues are associated with hydrogen embrittlement of steel as transportation, hydrogen or mixtures, natural gas with hydrogen. So, as you can see, a long-term operation causes a high sensitivity of steel to not only to brittle fracture resistance like impact strength, and also sensitivity to stress, corrosion, and cracking. Yes, this is a very dangerous phenomenon for pipeline stability. So, and dissipated damaging during long-term operation is the main factor for a loss of mechanical properties, especially brittle fracture resistance properties. And here you can see the most bright examples of operational damaging in pipe seals, which increase risk of structural integrity violation. And especially you can see a specimen after impact strength test and after usual tensile test, after simultaneous effect of operational degradation and hydrogen influence. So here you can see two ways of possible hydrogenation of pipe from internal surface. Two sources of hydrogenation: the hydrogen evolution under corrosion, it means electrochemical waste. And another way is the dissociation of molecular hydrogen into atoms, hydrogen atoms. So, and in our presentation, we consider some technological solution for test of specimens, and main of is holding of specimen in field condition, in tensile test. Here you can see a row of tensile test specimens in preliminary stressed state, and this block are placed into pipe with hydrogen atmosphere, long time, months, years, and we expect that during this long time, material will be hydrogenated and also possibly degraded due joint effect of stresses and hydrogen during so long time of holding specimens in field conditions. The main in this experiments, we should avoid of hydrogen desorption during when we take away specimens from pipe with hydrogen to test in laboratory conditions. It is very important, yes, because as we all know that we should prevent hydrogen desorption, so we should test specimens after holding off in pipe with hydrogen concentration which was in pipe during long-term holding of specimens in hydrogen atmosphere. So thank you for your attention.
Thank you to you. Are some questions? Okay, I have one question for you. In your opinion, what is the future of hydrogen transportation?
To my opinion, it is a great future for hydrogen transportation, because we have existed a network of gas transit gas pipelines. As you know, tendency is to decrease amount of transported natural gas, and we can transport together via our existing transit gas pipelines together mixture, smaller amount of natural gas with more and more amount of hydrogen. This is politics in Ukraine, that we try to organize commercially industrial production of hydrogen and transport such hydrogen via existing transit pipelines from Ukraine to West European countries, where hydrogen should be used more and more.
Thank you. Thank you very much for your speech. There is are there other questions? No? Okay, thank you.
Thank you very much.
Thank you to you. Okay, we have now the last presentation. After I recall the last presentation. The last is by Antunes, Borges, Neto, and Sergio. The title is Fatigue Crack Ground Residual Stresses versus Crack Closure. Antunes, thank you.
Hello.
To you.
You are listening to me? You are listening?
Yeah.
Okay. I'm going to share.
Thank you.
You can see?
Yeah, I see.
Okay, so let's do my presentation. Sorry. Okay. So the title is Fatigue Crack Growth, Residual Stresses versus Crack Closure. So there is a great debate about relative importance of residual stresses and crack closure. In this study, we consider the so-called Superblock 2020, which is composed of 8 load blocks separated by overloads. Note that there is a difference between the first and second block of the same type, because in the first case, there is an increase of the load, and in the second case, there is a decrease of the load from the maximum value of the overload. In the experimental results, we see that there is a difference between the 2 blocks of the same type. You can see, for example, B, the first block, and B, the second. There is a difference in a substantial difference in the crack increment. This is even more important in A, which is the lowest load range, as you can see in here. And now then we try to replicate this study numerically. You can see here the geometry of the city specimen, which we studied with and without contact of crack flanks. We considered the finite element mesh, as you can see, and we replicated the load patterns and material properties as much as possible. And in order to predict fatigue crack growth rate, we analyzed the cumulative plastic strain at crack tip. When this accumulation of plastic strain reach a critical value, the node is released and there is a crack propagation. The critical value is calibrated using one experimental value of the ADN. And you can see some of the results. We notice a difference between the first and second block of the same type as was observed experimentally. You can see in here, this is D1 is the first load block, D2 is the second. In the first case, the fatigue crack growth rate is nearly constant. In the second case, there is a decrease. When you remove the contact of crack flanks, which means that you are removing crack closure phenomena, the difference disappears, which means that now you have the same fatigue crack growth rate in both cases. Similar results were obtained for other load blocks. And in here, we compare the numerical prediction with the experimental results. The experimental results were obtained for another material. Anyway, there is a good agreement between both approaches, numerical and experimental. Note that in here, when you decrease the load range, there is an increase of the difference between the two load blocks. When we analyze the crack closure level, we saw that there is an excellent agreement between the variations of crack closure and the trends of the ADN. In the first block, there is no crack closure, and therefore the ADN is nearly constant. In the second block, there is a decrease of the ADN, which is explained by the increase of crack closure level. when we analyzed the residual stresses, we saw that these are not able to explain the ADN variations. At the beginning of the load blocks, you can see that the ADN is nearly constant, but the residual stresses are significantly different. On the other end, at the end of load block, where fatigue crack growth rate is different, you can see that the residual stresses are nearly similar. So the conclusion is that the residual stresses cannot explain the trends, and the crack closure is the main phenomena responsible for the trends we observed numerically and also experimentally. Okay, and that's all.
Thank you very much. I appreciate very much your work, and I see your long presentation. Are there some questions from the speakers, from other person, from our visitors? No? Okay. I have some questions for you. I don't understand what software did you use for the FEM model?
Okay, we have home developed software which is called DD3imp. Initially, it was developed to study deep drawing. Okay, but since it is very good in the modeling of crack tip of plastic deformation, we adapted it to the study of crack tip damage, assuming that fatigue crack growth is linked to cyclic plastic deformation at the crack tip.
Thank you, thank you for your answer. Okay, during your complete presentation, during slide 12, you say that there is a linear relation between the ratio of the crack increments and the load ratio. In your opinion, why?
We were not expecting such a beautiful trend. Okay, experimentally you can see that we obtained the same trend. Okay, the increase is expected. Okay, can be expected. The linear trend, I don't know honestly.
Okay,
it could be linear or other thing honestly.
Of course.
It is interesting. Now we intend to study other materials to see if the same trend is obtained. It is interesting, if you let me say, this load pattern is very interesting because the overloads are able to cut what happens before. You know, you are starting a new study, cleaning everything that happened before. It was developed by Professor Sundar from India, and I think it's a very interesting approach, honestly.
Okay, thank you very much. I have the last question for you. Do you think it is possible to formulate a complete analytic law for residual stresses versus crack closure? It's a hard question, I know.
You are asking if it is possible to develop a model?
Yeah, and a complete analytic law. Complete with the different material, with the different...
Oh, it's very complicated. The problem is that you have many variables. Okay, you have the material, you have the loads, you have the environment. You know, in material properties there are several parameters. It is not easy to obtain a model, an analytical model, able to capture everything. You know, there are many models in literature, some devoted to the load parameters, other including material parameters. But honestly, I don't think it is possible to have a full model for the ADN. That is the advantage of the numerical approach.
It's not easy. It's not possible, I think.
I don't think so. Honestly, I already tried to do something in that sense, but because some of the infos are very complicated. For example, the effect of Young modulus is linear on the ADN, but on the other end there are the kinematic hardening parameters, which are have a complex shape.
Of course,
it
of
was-
course.
Yes.
Thank you to you. Thank you for your presence here online.
you.
I think it
It's
is
a pleasure.
better in the next time to see in live. Okay.
Thank
Bye.
you.
Bye. Okay. We have lost four presentation. And we now I recall the last. Okay, the first of the last presentation is by Azadi Aro. I don't know if they are here. The title is Sensitivity Analysis of Stress, Pre-Corrosion Nanoparticles and Heat Treatment of Fatigue Lifetime of Aluminium Alloy. I think that they are not here online. And I see, Francesco, I read from Irina that she have some problem with the electricity, and if she can have a presentation in the other session. For us, is of course, for us, it's not a problem. Another day, yeah. Because can I make presentation later or another day? Later, of course. Another day, I don't know, in 31, I don't know she right here.
Hi, everybody. As we have many friends that has some problem, we will organize a special session dedicated to people that had problem with the connection and the electricity and so on. So don't worry, and we will organize something maybe at the end of the conference or, for example, on Tuesday. So don't worry, we will do that because we want to listen to you. We want you to join the conference. Thank you.
Okay, if there is not... okay. Okay, we can end our session number 7 now, and we can restart at 16 o'clock, not 16 and half.
One question, sorry. I think that is Schönborn is present in here. I think it's one of the presentations.
Who?
Schönborn, I think.
Schönborn, yeah. But Schönborn, can you hear me? Thank you. Thank you, Antunes.
Okay.
That Schönborn, yeah, it's online. I see you are right that Schönborn is here, but is online. But I think that he doesn't hear me. I think. Schönborn. Okay. There is some problem, I think. We try. Okay, see you at 16 o'clock. Bye. Have a good virtual coffee break.
Thank you.
Good to you.
Speaking. un Filippo online.
Posso partire?
Hi Filippo. I think the best thing to do is to check how many speakers are there, and then if you think that it's acceptable, you can start.
Okay, perfect.
Thank you.
So, dear authors, can I ask you if you are present? So, the first paper is validation and verification of fatigue assessment using FE analysis, a study case of notch cantilever beam. Is the author here? So is someone of the author paper 37, validation, verification of fatigue assessment using FEA analysis present? Okay. Is the author of fatigue analysis of engineering structure, state of development and achievement present? Okay. So is the author of fatigue of buried dented pipeline specimens present?
I'm here.
Thank you.
Yes, we are. Okay.
Yeah, perfect. And is Sabrina, Camilla, or Daniela or Andrea present for evaluation of fatigue strength and estimation of lifetime of ductile cast iron?
Sabrina is here.
Okay, perfect. And about the influence of residual stresses and fatigue on the fatigue endurance of structural components, is the author here? Chiocca, Frendo, or Bertini? Okay. And is Javad or Morten present to this section? Yeah, perfect. So we have 3/6. I think if you want, we can start. With the presenter that we have.
Yes, Phil.
Okay.
We are ready.
Okay, so if I'm not wrong, I think the first presenter that is here is one of the author of the paper of fatigue of buried dented pipeline specimens, and the authors are Victor Paiva, José Freire, Giancarlo González, Ronaldo Vieira, Alexander Ribeiro, and Ana Dalmeida. So I invite the first speaker to give a brief introduction of his work, and after that we will have, as usual, a short discussion with some questions about the topic. Thank you so much.
I believe the first author of the first papers just entered the section. I don't know if we want to start with him.
Yeah, okay, probably yes.
So if you can respect the order, there's no problem.
Yeah, okay. Is the author of validation and verification of fatigue assessment using FE analysis present? Is Aprianur Fairi present?
Yes, sir. Wait a minute, please. I'm sorry.
Okay, okay. So we will start from the first presentation instead. So we change. Thank you, Vitor, for letting us know. So I will introduce in the meantime the first presentation, which is validation and verification of fatigue assessment using FE analysis, a study case on the notch cantilever beam. The authors are Aprianur Fairi, Aditya Rio Prabowo, Eko Suroyo, Fitrian Imaduddin, Jung Ming Son, and Ristiyanto Adiputra. So I invite the first presenter to share a short presentation with the introduction of the topic, and after that we will have the discussion as usual. So Aprianur, the floor is yours. Yes?
Yes, sir. Thank you for valuable occasion, sir. May I share my screen now?
Yes, yes. You're welcome to make it.
Has my screen appeared? Sir?
Yeah, it's visible, and so you can put in the presentation mode.
Okay, thank you.
Or go ahead like this, it's up to you.
Yes.
Okay, now it's perfect.
Yes. Hello everyone, I am Aprian Fajri from 11 Maret University, Surakarta, Indonesia. On this occasion, I will show you my paper about validation and verification of fatigue assessment using finite element analysis, a study case on the notch cantilever beam. Estimate fatigue characteristic is essential to minimize the risk of catastrophic failure that may occur in the future. One of the methods is using finite element-based simulation, and benchmarking with other research aims to validate the simulation procedures that have been used. Similar research was conducted by Coxall et al. In 2013. The material used is structural steel with an endurance limit of 86.2 megapascal. The simulation setup can be seen in the figure. The loading applied is zero base with a magnitude of 10 kilonewton. And then in the recent research, the stress component used is for meso stress, and because the loading scenario is not a zero mean, several mean stress theories are needed to correct the stress amplitude. Based on the convergence analysis, the mesh used in this study is 4 millimeter. And the benchmarking result has a small error so that this procedure is valid and can be used for the following research. Thank you, sir.
Yeah, so thank you so much. Are there any questions from the audience? So please don't be shy, otherwise I will make some questions. So please, if you have questions, let us know. So there are no questions, so I will make some questions to you. And the first one is if you evaluate the mesh sensitivity for applying your criterion, because I think that is a bit important for this case. So have you considered different mesh size, or you always fixed the same size?
I use the different mesh size, sir. So the consideration of the mesh size that I choose is time required for one simulation and the value, sir.
Okay.
And I use the mesh refinement on the hotspot stress, like this.
Okay. And about the shape of the notch that you select, you studied only one sharp notch, or your intention is also to extend the approach to blunt notches?
I use the form of parabolic tetrahedral with improved quality in areas suspected of stress concentration, sir. Only one form.
Okay. And
Yes.
you see here, you say here that that your study is dedicated to fatigue, right?
Yes, sir.
Yeah. So why did you use the von Mises stress? I mean, usually von Mises is mainly used for static failures, but is there any specific reason for selecting von Mises instead of any other stress?
Yes, sir. Because based on the literature review that I have done, the von Mises stress can be used for this condition, sir, and has the value is uh, best for this condition like
Okay.
this.
Okay. So thank you very much. I don't have any other question. So I think you are also the speaker of the second presentation. I'm right?
Yes, sir.
Okay. So I think you can simply share the next presentation. The title of this presentation is Fatigue Analysis of Engineering Structures, State of Development and Achievement. And the authors are the same, are different, so I have to read them. Priyanur Fairi is the first author, Aditya Rio, and after that Nurul Muayat, Daru Febi Smaradana, Aldias Batmaka. So these are the authors. So you can share again your screen and make a brief introduction also of this topic. Thank you so much.
Okay, sir. Okay, sir. Has my screen appeared, sir?
Yes, it's perfect.
Okay, thank you, sir.
Again, you have to put in the exactly fine.
Yes. Thank you. I am April Fajri. On this second opportunity, I will tell you my review paper about fatigue analysis of engineering structure, state of development and achievement. Fatigue failure is a phenomenon that often occurs in mechanical structures, especially in components that receive direct cyclic load. For example, marine facilities, automobiles, critical infrastructures, reservoirs, turbines, nuclear reactors, and features that work in extreme conditions. The fatigue phenomena causes about 80 to 90% of engineering material failures. Several factors can affect fatigue resistance and must be considered when designing a structure. Research on fatigue started more than centuries ago. Until 1961, a new method known as fatigue crack growth was discovered by Paul Crochy-Parrish. Currently, several approaches can be used to analyze fatigue in structures. This approach can be divided into two types based on the basic assumption, the presence or the absence of initial crack. Thank you.
Okay, thank you so much. Is there any question to the speaker? You're welcome to make questions. So if there are no questions from the audience, I can make some. So you have shown that there are criteria that are working well with the crack and criteria that are working well for a component without a crack. So I would like to know your opinion about the criteria that you consider more promising with the crack, according to your experience, and which is the trend in this direction for the future. So a kind of future perspective for some useful criteria that we should consider in presence of cracks.
Okay, thank you, sir. There are several factors to determine the approach that must be used. If the condition is no crack initiation, we can use a frequency-based stress life approach or strain life approach. The criteria is when the condition is low stress and high cycle, and the areas is elastic load, we can use the stress life approach. And several mean stress theory can be used is Goodman, Söderberg, Gerber, and ISME elliptical. Goodman and Söderberg is best suitable for the ductile material, and Gerber or ISME is best for the other material. And then if the condition is low and high stress, but low and high cycle, elastic and plastic load, we can use strain life approach. And mean stress theory can that we can use is Morrow criterion or Smith-Watson-Tropper criterion. And then if the condition on the structure has initial crack, we can use the fracture mechanic to predict the fatigue crack propagation on the crack, like this, sir.
Yeah. And the last question is, have you also interest in the multi-axial fatigue problems? Have you made a kind of review also on these criteria, or you are mainly focused on uniaxial fatigue?
When we talk about structure, so the stress condition is usually about multi-axial fatigue load, sir. So I interest in this because this is has the yes, I mean, when we talk about structure, we must consider about multi-axial fatigue load, like this, sir.
Okay, okay. So thank you so much again for this interesting review. And of course, I wish you the best for your future research. So I think we can
thank you, sir.
Yeah, you're welcome. Yes. So I think we can move to the third speaker of this section. That is Vitor. Yeah, that is present from before. Yeah, the title is Fatigue of Buried Dented Pipeline Specimens. The authors are Vitor Paiva, José Freire, Giancarlo González, Ronaldo Vieira, Alexandre Ribeiro, and Ana Almeida. I hope I pronunciate them well. So you are welcome to share your screen and to share with us your slides or your small presentation.
I believe you're all seeing it.
Yes.
Hello, everyone. My name is Vitor Eboli. I'm from PUC-Rio, and I'm going to briefly talk about our work. That's fatigue of buried dent pipeline specimens. Fatigue of pipelines is not new, and that's the type of defects that the pipeline can have due to indentation or rock or soil movimentation. So this is an extensive study that studies the effects of dents in pipelines, and I'm gonna present to you just a part of it because we studied specimens in air, specimens that were buried, and 16 specimens that were tested in air, and also repaired with composite material. So as you can see over here, I believe you can see. Sorry, as you can see here, the specimen is a 3 longer meter pipe. We have a longitudinal dent that was created with an indenter and a servohydraulic machine. We used fiber optic interrogators in the dent area and also GC. and a cyclical machine to apply pressure in the pipeline specimen. The specimens that were buried here, we want to show the results of the specimens that were buried and compare with those that were tested in the air. So the specimens that were buried were first tested in air. So we apply 5 cycles of distributive pressure of 60 bars. And after that, we measure the strain maps with DAC, as you can see here, the DAC pattern. And from the results from the DAC, we plug the fiber optic sensors in the critical positions of where we expect to have a crack. In this case, is the edges of the dents over here. And after that, we repeat the same procedure of 5 cycles of pressurization with the same pressure to compare the DAC results with the fiber optic strain gauge results. In this case, the circumferential results. And after that, we bury the specimens in soil and apply the same pressurization cycles of 60 bars. In this case here, I will only show 3 cycles, but we have done 5 cycles, and compare the results before burying and after burying the pipe with the DAC and the fiber optic strain gauge. As you can see over here, the levels of strains are very similar, showing that the soil do not offer any benefit, any increase of life, any increase of restriction in the dent area. So there's no evidence that the soil will improve the fatigue life of the dent. And with these results of the circumferential strains, we were able to plot a Kaufman-Munson equation with the actual fatigue tests lives that we measured for the specimens in the air and the buried specimens. And they agreed well with the Kaufman-Munson equation. They're very similar. So you can predict the life of the pipeline specimens using a Kaufman-Munson equation, and the soil will not offer any significant interference in the effect of the displacement of the dent. So this conclusion of this paper is that we combine a set of 2 experimental techniques like the DAC, digital image correlation, and fiber optic strain gauge, and we were able to predict the life of the buried specimens with the dents using a simple Kaufman-Munson equation, and also the soil did not influence the life of the specimens. So I believe I have done all. That's about it.
Yeah. So thank you so much for your nice presentation, for the nice topic. Are there questions from the audience? Okay. So if there are no questions, I would like to ask you some curiosity. The first one is, I have seen that you have used different monitoring approaches in parallel to monitor the structure of the pipe. So usually the setup of this is quite difficult, and I would like to know your experience with this, because from my experience, for example, to use DIC is not always very easy, and I want to understand from your point of view if you have some issues with the setup of everything was quite straightforward and easy.
This project we initiated in 2007. So we have a lot to learn with the DAC combination with strain gauge, and we gain a lot of experience. So in the beginning was very difficult. The hardest part was to put the specimen with the connected to the hydraulic machine. After that, we were able to control the pressure, measure the DAC, because we have a load cell we can measure the pressure with the DAC output. So we can correlate the strains with the exact pressure. After that, we were able to place the strain gauge and repeat that. And you can see over here that we also use a thermal camera but not in this paper specifically. We include these results, but in all the others tested in here, we use the thermal camera to analyze the specimen's behavior during the fatigue tests. So we were able to see the crack growth and how the specimen was behaving, because we use TSA. I don't know if you know, but it's thermoelastic stress analysis that you can measure the first invariant of stress. So we were able to compare this, like this. Here's is the DAC image with the infrared camera, and also after that with the strain gauge results.
Okay, so thank you so much. I would like also to ask another curiosity, that is, I think you made a very good job here with this work, but which is the future plan that you have for going on with this activity? So which is the future development of this activity?
Nowadays we tested a total of 33 specimens. 9 were tested in the air, like this one, and 8 were buried. Were tested in the air, then buried, and 16 were repaired with 3 types of composite materials. Some of these tests take around 1 million cycles. This is about 3 months to complete. So today we are finishing the last specimens, and we are thinking about the future, what we're gonna do with these results and how we will present them.
Okay, so thank you so much for the nice work. Really impressive, the setup and the activity. So thank you again for being with us.
Thank you.
Yeah, so now we have the 4th speaker of this section that I think is in presence. And the title of the work is Evaluation of Fatigue Strength and the Estimation of Lifetime of Ductile Cast Iron Under Multi-Axial Loading. The authors are Sabrina Vantadori, Camilla Ronchey, Daniela Scorza, and Andrea Zanichelli. And the presenter is Sabrina Vantadori. So welcome.
Okay, grazie. Thank you, Filippo. Good afternoon, everybody. The goal of the present research is to estimate both fatigue strength and lifetime of ductile cast iron smooth specimens under multi-axial cyclic loading by means of the multi-axial critical plane-based criterion proposed by Carpentieri and others. Although the accuracy of such a criterion has been extensively assessed for steel, aluminum and titanium alloys and gray cast irons, simulations involving DCI haven't been so far performed. Therefore, 2 experimental campaigns available in the literature have been simulated, and more precisely, the experimental data examined are related to both infinite and finite fatigue life multi-axial tests under proportional and non-proportional loading. It has been shown that with the multi-axial criterion employed, a quite satisfactory accuracy in the evaluation of fatigue endurance condition has been achieved. Moreover, for finite fatigue life test, the number of loading cycle to failure has been estimated with a satisfactory accuracy far greater than that related to other multi-axial criteria available in the literature. Okay, thank you for your kind attention.
So thank you for the presentation, and I ask to the audience if they have questions, please. no question from the audience, so I will ask you some curiosity. The first one is I have seen here that you have applied the criterion to notch specimens for plane specimens. Is there any plan to make a kind of extensive work later on notch samples, and how you will approach this problem in the case?
Yes. The criterion was applied in the case of notched specimen and also fretted specimens together with one of the three methods falling.
Okay.
One of the three methods related to the critical distance, and in particular the point method and the line method. The results obtained were quite satisfactory, both in the case of notched specimens and in the case of fretted specimens.
Okay, thank you so much. And I want to ask another curiosity. How can you consider the scale effect in your criterion for fatigue prediction? So is possible to have different scales of samples and make a good prediction, or you have to change something in the criterion to adapt it to different size? It's only a curiosity. I don't know the answer actually.
No, it's not possible to take into account the scale effect.
Okay, perfect. And the last curiosity is about the future work that you want to perform in this regard. Have you a plan for future activities in this field, and why
yes.
or how you want to perform this?
Yes, I'm studying what happens, which is the influence of non-metallic inclusions, especially for high strength steel, and in particular the influence of such inclusions are related to the fatigue limits. I'm trying to modify such fatigue limits, because the criterion is a critical plane-based criterion, where the orientation of such a criterion is linked to an off angle named delta that is computed by using an empirical equation that depends on the fully reverse fatigue strength at a given number of loading cycles or fatigue limits under normal stress and shear stress. And each of such limits depend on the presence of non-metallic inclusions, especially for high strength steels. And so we are trying to evaluate the accuracy of the criterion when such a type of defects are present in steels by using the well-known equation of Murakami, and for the first one is for normal stress, but then it was extended also for shear stress.
Thank you so much. And congratulations for the nice work. And yeah, so I think we can go to the next speaker.
Thank you.
Thank you. So the title of the next presentation is Influence of Residual Stresses on the Fatigue Endurance of Structural Components. The authors are Chiocca, Frendo, and Bertini from Pisa, I think. And
yes.
So I invite
Good afternoon.
and I think Andrea.
Yes.
Right. Yeah, to give the presentation.
Okay, I will try to share the screen.
Yeah, thank you.
Okay, sorry, but
no,
okay.
It's not.
It's my first time with Zoom, so
yeah, there is share screen. Yes, perfect.
Okay.
And after that, you can put in presentation mode.
Yeah, sorry. Here.
Yeah, it's
okay.
coming.
Can you see
yes.
the presentation?
Yes, now yes, it's
okay.
Perfect.
So I tried to create a short presentation. Good afternoon to everyone. I'm Andrea Chiocca, a PhD student from Industrial Engineer of the University of Pisa. And today I will present my part of my project during the PhD course. This is dealing with the study of the influence of residual stresses on the fatigue endurance of structural components. So what we studied here was tube-to-plate welded joint and a notch specimen. So first of all, we tried to understand what was the influence of residual stresses on the welded joint, both from an experimental and a numerical point of view. And what we are doing now is trying to, say, translate the results we had on the welded joint also for the notch specimens. So to be able to better control the residual stress field, so we can create the residual stress field. And we are trying to reach the same results. So dealing with the welded joint, we made some say numerical studies. First of all, we did a numerical simulation, a thermostructural numerical simulation, to be able to at least have an idea of the residual stresses. So we calculated residual stresses, and then we mapped these stresses for a fatigue analysis, also from a numerical point of view. So we initialized residual stresses, and I say we calculated some fatigue damage factors. Precisely in this case, we calculated some critical pain factors for the critical section, and only for, say, who is interested, the critical point here was the weld roots. So all the critical pain factors here, both for bending and torsion, were evaluated in the weld roots. So the main results here was a different behavior in pure bending and pure torsion. So after relieving some specimens, we highlighted a different behavior. So during pure torsion, the fatigue life, let's say, was increased. At the moment, we don't have so many results, but so also the experimental part is still an ongoing project. On the contrary, for the bending part, we noticed no difference between the relieving process and the as welded specimen. So having the numerical model, so having the numerical residual stresses, we were able also to evaluate from a numerical point of view if this difference was existing from also like a critical plane factor point of view. And we noticed the same thing. So as you can see, I reported here the maximum relative error, and this is around 8% for the pure bending. And this is around the maximum one is around 30% for the pure torsion. I have to say that for pure torsion, the error was always greater than 15%. So in the case of bending, it depends on the load. So, okay, we did also this for other critical plane factors, and we noticed the same behavior. So let's say that a factor that as say can describe this this behavior at the moment is the stress axiality. So we noticed that in the case of pure torsion, nominally the hydrostatic stress should be 0, and instead, when you introduce residual stresses, this hydrostatic stress, let's say, change. So can have an influence on the, let's say, the final fatigue life of the specimens, while in the case of pure bending, the stress discharge factor was nearly the same for both as welded and stress relieved condition. So what we are also trying to do now with this notch specimen is to control the, say, the residual stress inside the specimen. And at the moment, we are doing different tests. So both by pre-compressing the specimens and then, let's say, using fatigue loading, torsion, and tensile, or using, let's say, a constant tensile loading, and then, let's say, using the fatigue loading. In this case, we are, let's say, changing the load ratio. And so I only have the results at the moment for pure torsion loading with a tensile static loading of 10 kilonewton. And say, we could expect that, but the fatigue life is increasing if we are not, let's say, if we are not loading the specimen. So what we are doing now is to compare all the results and try to understand if we can replicate what we saw with the welded joint. Okay, I finish here. The notch specimens, so the geometry was made to replicate in some ways the notch made from the weld seam, let's say. So the radius is the smallest possible we could, let's say, design, and also the angle of the notch. So to have, let's say, the same plastic region compared to the welded joint. So the main conclusions here are, okay, there is an effect made by the load, if it's pure torsion or pure loading, say in presence of residual stresses or not. So we are trying to understand what are the main parameters that are affecting this behavior, and by using, let's say, a simple specimen where we can control more, because usually with welding, it's really difficult to have a full control of what is happening, say, in the region of the weld seam. So thank you, everyone. And if you have questions, please feel free to ask.
Thank you so much, Andrea. If the audience has questions, they are welcome to make questions to the presenter.
I have a curiosity, Filippo.
Yes, go ahead, Paolo. You're welcome.
Thank you. And my congratulations, first of all, for the presentation and this very interesting work. I'm wondering if you consider phase transformation when you perform a numerical simulation.
Okay, thank you for the question, because this is a good point. Not at the moment. I will say, first of all, we not consider phase transformation because of the material we are using. It's a low carbon steel, so the phase transformation is not, I would say, not so important for a first case study we are doing here. Of course, to refine the model, I mean the numerical model, it's necessary to include phase transformation. So let's say the idea was to reach the final part to get the residual stresses and to be able to understand if the experimental results we had were something we could extract also from a numerical point of view. At that point, we are able also to refine the numerical model, because let's say we had some good results also from a numerical point of view, even with this numerical model. Let's say the numerical model, I didn't describe so much the numerical model, but all the work behind it was to simplify the numerical simulation. So we use not a classical thermal model like thermal sources like Gaussian or Goldak. We use the really easy one. So we say activated elements at a one temperature. So it was really easy. And there were already a lot of hypotheses in this model. So not considering the phase transformation was inside the model at that point. But yeah, this is a really good point. So it's something we have in mind, and we have to, let's say, solve this problem at one point. So thank you very much.
Well, you're welcome. It should be important, in my opinion, to validate the model using experimental measurements of residual stresses.
Yeah, until now, we say validated the model with relaxed strains. So also I didn't describe so much the numerical model here, but we used strain results to validate the numerical model.
Okay.
At that point. But yeah, of course, to introduce the phase transformation from a point of view, we should refine the numerical model more, because at the moment it's so simplified that it has a lot of simplification inside. Also, so the phase transformation is something that is adding some more, let's say, chaos, but is not solving a lot because of the, say, how the model was designed until now. So it's only a problem of the model design that was really simple design. But of course, if we are refining the model, it's necessary also to include phase transformation.
Yes, I got. Thank you very much.
Yeah. So thank you very much. I also agree with Paolo that your work is quite impressive. It's touching a very important topic. And I have also a question for you. I have seen that you have made some experimental results under bending and under torsion.
Yeah.
So did you detect during the test a different behavior a different behavior in terms of plasticity under torsion and bending? And that can be correlated with the different slopes of the curve that you found in the fatigue results?
Let's say it was difficult to first of all detect the crack. In these kind of specimens, we used let's say a pressured chamber to detect the through the thickness crack.
Okay.
And for some specimens, we break down the specimen to have like a good visualization of the crack. And one point was that sometimes the crack initiation point was changing from specimen to another, but I will say 90% of the time was starting always in the weld root.
Okay.
For torsion, like 100%. For bending, in some cases, the crack was starting from the weld toe. So let's say the weld toe, the low weld toe. And I think that let's say the crack's initiation point, it's difficult to say why something like this is happening, but for sure it's correlated with the different geometry of each specimen from, let's say, a weld seam point of view. And so at the moment, we never focused too much on the, say, what was happening closely. We were testing the specimen. Once the pressure chamber was emptying itself, for us, it was like broken. And so we never really focused too much on the, say, from a crack point of view, because it's difficult with this kind of specimens.
Okay. And the last small question or quick question is about the life of the specimen. So during the test, the fatigue life was mainly spent in initiation or propagation? I mean, or have you a kind of estimation of this percentage? Because I mean, that is also interesting. If the crack is only propagating and the initiation phase is very small, we have to rearrange the fatigue prediction criteria that we will use later. So I think it's nice to have at least a kind of rough estimation of this.
Yeah.
Have you an idea of this, or?
Thank you for the question, because this is another, let's say, critical point for example, the critical plane factor we used, because let's say it's a problem to use it when we have like a long propagation phase. Exactly. I would say no. And I don't know if Professor Frendo is here listening, but he followed most of the experimental part. So I'm the one that is using his results.
Okay.
And I think I'm not the best person here to explain the part. So I'm sorry for this.
No, it's perfect. But it was only a curiosity, because actually I'm very interested on the topic, and I think we can share opinions also outside this conference, and probably also reuse these results for future applications. Also, Paolo is working on this topic, and so we are very interested on this. And so thank you so much for the nice presentation.
Thank you. Thank you.
Thank you. So I think we can go now to the next speaker, which is the last of these 8 sections. And the title of the work is Fatigue Behavior of Geometrical Tailored Components. The authors are from Norway, from my department. The first author is Javad Razavi, associate professor in my department, and the second author is Morten Jorgensen, that is a student working with him. So I leave the floor to, I think, Javad.
Thank you, Filippo. Hello, everyone. I'm very happy to present some preliminary results from this work that we have done with the master student that I have here, Morten Jorgensen. The plan was for him to present the work, but yeah, it changed somehow. So I'm going to present it. I have to first share the screen. Okay, do you see my screen now?
Yes, yes, perfect. Okay. It's perfect, Javad.
So this is a presentation on a quite simple topic. So between these advanced topics that are being presented in the conference, it's good sometimes to have fun with some very simple ideas. It's mainly toward design and somehow correlating it to what we know from fatigue. So the typical thing that we know from the stress analysis, let's go for a simple case. If we have a plate which it doesn't have any notch or geometrical discontinuities, the stress flaws are usually parallel lines, and the distance or the density between them is almost uniform. So here, if you look at the stress distribution in the gray area, you can see that it's quite uniform. In the same plate, if we introduce a circular notch in the center, we can see that on the edges of the notch, the stress raises, which is quite normal. And obviously in that area, we have a higher density of the stress flaws, and the lines are getting closer to each other. This eventually would result in a factor that we call it stress concentration factor, higher than 1. So in this project, we were thinking about how to reduce the stress concentration in the component without changing the overall geometry of the part, outer geometry of the part, and also the geometry of the notch. So we want the geometry of the notch to be constant and somehow manipulate this stress flaws in the component to reduce the maximum stress ahead of the notch. For this aim, we created 4 batches of specimens, 4 different geometries. The control geometry is a specimen in the form of a duct bone with a circular notch in the center that has a diameter of 5. It can be a little bit small, but this geometry, it has a diameter of 5, the notch in the center. And we added some additional geometries. Here you can see a quartile of the overall geometry. So in the geometry that is called notch 3, we added 1 additional notch on both sides of the main notch. So the main notch had a diameter of 5. We added this secondary notch with a diameter of 3. And the variable here in this geometry was the distance between these 2 adjacent notches and our main notch. So the parameter V. And we had values of 2, 3, and 4 millimeter. We had other cases of which are called notch 5 and notch 7. This number actually shows in total how many notches do you have in the sample. So when we have notch 5, it means that we have 1 main notch and 2 additional notches on each side of this center notch that we have. In this case, what we thought was that, okay, the added notches in the sample is quite large. It's 3 millimeter compared to 5 millimeter. It's quite large. How about reducing it and dividing it in 2? So instead of having 1 notch with diameter of 3, we added 2 notches on each side with a diameter of 1.5 millimeter. And in the third case, on each side of the main notch, we had 3 added notches. In all 3 cases, the variable has been considered to be V, or the distance between the 2 notches. I need to mention that in the cases of notch 5 and notch 7, the added notches were added in a way
to have their edge in the same line as the edge of the main notch. Okay, so these are the three cases that we had, and we wanted to see how this added notch is going to change the maximum stress ahead of the notch. We performed some finite element analysis on, again, 1/4 of the geometry because of the double symmetry that we had. And the results showed that comparing the results of the specimens with more than one notch in them, they all had reduction of the maximum stress ahead of the notch. So the reduction is not that high, it's around 10%, but they all experienced the same thing. Where we had one added notches on each side, by changing the distance, the maximum stress didn't change significantly. The changes were quite small, and that was somehow disappointing for us. But for the other two cases, by increasing the distance, we had higher stresses. So obviously we could see that when the notch is closer to the main notch, it's affecting it more. But this was the stress analysis. We couldn't get any conclusion from it. So we performed some preliminary fatigue analysis on this, on the samples that were fabricated using this geometry. The samples were made of aluminum alloy, and they were machined to the geometries that we had them. So here you can see the results of the fatigue test in all cases, including the control specimen. The applied load was kept constant, 4.5 kilonewton as the maximum stress, and the frequency was 20 hertz. You can see that in all cases, we had an increase of fatigue life from around 100,000 for the control specimen with only circular notch to even up to 300,000 for at least one of the cases in each batch. So this doesn't quite follow what we saw in the linear elastic analysis that we performed, but overall, it was quite hopeful for us to see that even by adding a small notch that has a radius of 0.7 millimeter, somewhere around the main notch, we could manage to increase the fatigue life 3 times. Of course, this is not a general statement. This enhancement can depend on so many different variables, including the load level. So obviously, if we are having a higher load level, we should expect lower enhancement of the fatigue life because of the possible plastic deformation that can be caused in the geometry and in the sample. But overall, in the 2 load levels that we had, I'm presenting one of them now. In both cases, the enhancement of the fatigue life was quite significant. One thing that we observed was that, okay, we saw that when the notches were closer, in the case of notch 5 and notch 7, were closer to the main notch, the stress was showing to be quite smaller. But that caused an issue for us, that the crack after initiating from the main notch, it was approaching the adjacent notch. And eventually that resulted in lower fatigue life than what we expected. So overall, by keeping the distance in a reasonable place, we could get even a little bit higher than 3 times the fatigue life that we got. But what was the reason for drilling some holes in a sample that already has notch and testing it on the fatigue? So the goal was not obviously to have geometries like this. This was some sort of a benchmark for our future work, where we are incorporating lattice structures in the main geometry that we had. By doing so, we are hoping to somehow manipulate both the stiffness of the component and also the stress state around the main notch to be able to get higher fatigue lives. At the moment, these samples have been designed and fabricated, and but so far we haven't been able to test them. But hopefully we are hoping to get also interesting results from this case. One thing that I should mention is that the case has been,
yeah, because you are making 20 minutes.
Yes, I try to put only one slide to make it short. Yeah.
No, it's very good actually. It's fantastic, but
thank you. Yeah, just the last statement. The main thing that should be considered is that the loading in all these cases is axial. So obviously, if you have a little bit of misalignment or a complicated loading case, this can go ballistic. So it would obviously require additional studies in future. I'm ready for any question on the topic.
Yeah, so thank you so much, Javad. I hope that there is at least a question from the audience. We have time for one question, so I leave the audience to make it. Paolo, do you have some questions? You are muted, Paolo.
Just a moment. Professor Cornetti, please. Sit down.
Okay. Hi, Filippo. Okay.
Hi.
I'm Pietro. So just a question for Javad, very interesting talk. Maybe you mentioned, and I missed, just if you have some explanation why the stress concentration sometimes is not varying very much, while the fatigue life is highly changing from specimen to specimen. Just some more comment. Thanks.
Thank you so much. It's actually a very good question, and it was something that I was not expecting at the beginning as well. But as you can see also, we have only 2 specimens tested for each condition, and for fatigue, that doesn't make sense. So
Ciao a tutti.
Sì, è caduta la linea.
Sì.
Javad?
Linea dalla...
Sì, andati lunghi, penso. Siamo andati lunghi.
Linea dalla...
Sì, andati lunghi. Siamo andati lunghi.
Linea dalla...
Sì, andati lunghi. Sì.
Chi è che gestisce i microfoni? I microfoni? Ok.
Hello.
Hi, Filippo.
Hello, I think that there was a shutdown of the connection from Norway. So actually I'm connected with the mobile. Hello, I think that there was a shutdown of the connection from Norway. So I think we have to postpone the questions of Javad in the next time. So I'm not able to go ahead with these questions now.
Okay.
Can you hear me?
Yes.
Yes.
Yeah.
Okay.
Yeah. So I think Pietro, you can contact directly Javad for the question, and you can discuss with him. And okay. I think now we have 2 presentations from the previous section that were not delivered. Especially, I want to understand if Uzov is here for the presentations or no. Otherwise, I think we can close this section.
It's me, Sergey.
Yes.
Yes, I'm here.
So yeah, you can make your presentation.
Yes. Yes, I can.
Actually, I didn't. To be honest, I didn't watch your presentation, so because you were not in this section. But we will make in any case. Go ahead.
So do you see the title?
Yeah, it's perfect.
Okay. I'm sorry, we had a problem with internet connection, so I will make this presentation now. Good evening, everyone. My presentation will be about dynamic and quasi-static interlaminar shear strength of carbon fiber laminates under biaxial loading conditions. Motivation. In order to predict behavior of real structures, we have to know elastic constants and strength parameters of a composite, because and we have to test it in various directions because laminates are highly anisotropic material. So how we did it? We reach biaxial loading conditions because our specimen, as I said, are highly anisotropic. So under compressive load, specimen wants to change its shape, but due to friction force, it keeps keep it in initial state, and we have combination of two forces, compressive and friction force. And we can also change layer orientation, so we can cut our specimen from a different direction and change this level of anisotropy. And we have done two types of tests: quasi-static on Shimizu AGX plus testing machine. As you see, specimen is coated for DAC tests, and also dynamic tests using split Hopkinson pressure bar. In this test, we also did high-speed filming, and you can see, for example, crack initiation, early stage of crack initiation. So crack was initiated at upper right corner and propagates downwards. And we have done this test at different layer orientation, at different strain rates, and found that shear strength is more or less independent on the layer orientation in the if you especially if you keep in mind the scatter of results. But so here shear strength varied maybe 2 times, but compressive strength of specimen was varied by almost 4 times. So we found that shear strength is much less dependent on the compressive force than, for example, friction force in the same condition. And in dynamic tests, we found that friction force is not enough to keep specimen in desired state. So as a future work, we have planned to design a different type of clamps, for example, maybe as in this paper, in order to better control of specimen position. So finished. So if you have
Thank
any
you.
questions.
Thank you so much for the nice presentation. Are there questions about this work? We have time for one question from the audience. So if there is no question, I think I can have one. Have you considered the possibility to study different scales of these problems? Because at the moment you are focused only, I mean, not only, but you are focused on one specific scale. Do you expect difference changing the scale?
Yes, yes. For example, we can do some kind of notch in order to reduce area of the process. It is quite easy to change scale in quasi-static loading because here maybe we can test 4 times larger specimen, but in dynamic we have
a limitation.
Yeah, we have limitation, and it is quite hard to increase diameter of Hopkinson pressure bar because if we increase diameter, then we have to increase length, but we are limited to the area. In our case, total length of our setup is something around 8 meters. So if we want to increase scale of the specimen twice, we have also increased the length of our setup, maybe
Okay.
not twice, but something around.
Yeah. Thank you so much. So I think you are also author of a second work that missed the previous section. I'm right?
Yes, but I think I have no her presentation here. I think she decided to make her presentation tomorrow.
Okay,
My
okay,
colleague,
perfect.
yes.
Yeah, it's perfect, yes. Okay. So I want to thank you for the nice contribution. I think we can conclude with this presentation, this section, which is the last of this day. And so thank you so much to all the speakers, and I wish you a pleasant evening and a pleasant dinner. So thank you so much to all.
Thank you.
Thank you. Bye.
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 Okay. Hi, everybody. I wish to thank all of you for your participation. And now, in 5 minutes, we will start the meeting of the IGF members. All the meeting will be held in Italian. So if you want to stay with us, it will be a pleasure. But due to the Italian laws, we will be forced to use this language for our national meeting. So if you want to stay, no problem, but starting from this moment, we will start using Italian. Ok, buongiorno a tutti, qualche minuto iniziamo, ok? Un secondo per far permettere a tutti di collegarsi. Permettere a tutti di collegarsi.